Let's try do another example of the area bounded by the graphs of f of x equals the cube root of x minus 1 and g of x equals x minus 1. Now we're going to sketch the graphs and show how to divide up the intervals for the total area between the two curves. All right, well, of course, to help me find this, I would want to know what each of these graphs look like. I know what the cube root of x looks like. In fact, it is a cube root curve shifted to the right by 1. And I know what my curve y equals x minus 1 looks like. It's a linear function, a line, with a y-intercept at 0, -1, and a slope of 1. So I could graph those two together, and doing so gives me this particular shape. Again, uh, if I'm unfamiliar with some of my graphing, I might be interested in going through and reviewing how to do that the graphing methods right here. But let's talk about how do we find the points of intersection and assure ourselves, other than what we see on the graph, that that's what's happening. Well, in this case, we would solve this by taking let me put this in a different color here, by taking the cube root of x minus 1 and setting it equal to the quantity x minus 1. So if we're solving this, well, cube roots are kind of hard to deal with, and they're kind of notoriously unfun for most people. So what we're going to do is we're going to cube both sides of the equation, and doing so is going to reveal that x minus 1 would equal the quantity x minus 1 cubed. Now, you can go ahead and carry out this cube if you really wanted to, but I'm going to show you that it's not really necessary, because we can take this equation now and treat it as a polynomial of a single variable. Our single variable is going to be the quantity x minus 1. Here's what that looks like. I've got 0 would equal the quantity x minus 1 cubed minus the quantity x minus 1. And if it helps, you can write it as x minus 1 to the first. Right? There's a common factor here. Easily enough, you see that x minus 1 can be factored out of both of those quantities and give us x minus 1 to the second minus, well, x minus 1 factored away from itself is just 1. And a little bit of simplification would reveal that we get x minus 1 times the quantity x squared minus 2x plus 1 minus 1. So it's just x squared minus 2x. And we get x minus 1 times x minus 2. And I'm going to factor x out of these two terms times x. So we get three factors here set equal to 0. That means that our points of intersection are going to be at x equals 1, as we suspected it would be right here. At x equals 2, which maybe we expected or maybe we didn't, but there it is. According to our graph, that seems to fit the situation. And of course, x equals 0 over here at the point 0, -1. Of course, knowing which graph is which is kind of important to us. This graph here in yellow, right here, that is g of x equals x minus 1. Of course, this curve right here in red is f of x equals the cube root of x. So on the interval from 0 to 1, we see that g is greater than or equal to f. Now we could certainly go through and verify this by choosing a number on the interval between 0 and 1 and just testing, right? We could say that, all right, if we are on the interval between 0 and 1, we would substitute in some value to see which is greater or which is less, and we would see that f of x would turn out to be less than g of x on that interval, just by substitution, right? You choose 1/2. The cube root of 1/2 minus 1 is going to be less than 1/2 minus 1. On the other hand, if we go on the interval from 1 to 2, we're going to see that f is greater than g, greater than or equal to g. Again, a substitution trick on that interval from 1 to 2 is going to show us that in that case, g of x through substitution would be greater than, would be less than, not greater than, we've already been there, would be less than or equal to f of x. Well, less than, because if we're in between those 2 points, that would certainly happen. Okay, so just like before, we're going to set up an integral that gives us this area between the two curves by us taking, in the first case, g of x minus f of x, and then taking f of x minus g of. So we're going to take the sum of the integral from 0 to 1 of the quantity x minus 1 minus x minus 1 to the 1/3 dx, plus the definite integral from 1 to 2 of x minus 1 to the 1/3 minus the quantity x minus 1 dx. All right, so this integral isn't too bad. It might take us a little bit of work, but I think we can get this one reasonably well. We should have the following. We're going to have 1/2 of x squared minus x minus 3/4 of the quantity x minus 1 to the 4/3. Now, of course, we would try and do this by substitution. We see that x minus 1 would be our u, but of course du would be dx. So this is just going to work out directly. And we're going to add just sort of the reverse of that that set of terms right there, this time evaluated from 1 to 2. Making some substitutions is going to reveal the following. We're going to have 1/2 times 1 squared minus 1 minus 3/4 of 1 minus 1 to the 4/3. Well, that's just 0. Minus 1/2 times 0 minus 0 minus 3/4 of 1. Well, negative 1 to the 4/3. That's positive 1. We're going to add to that 3/4 of 1 to the 4/3. If we take 2 minus 1, that's 1. Minus 1/2 of 2 squared, which is 4, plus 2, minus the quantity, 3/4 of 0 minus 1/2 times 1 plus 1. I'm going to continue to simplify here a little bit just to make my life easier. Of course, we see that if we take 1/2 minus 1, we're minus 0, we're going to get negative 1/2 minus 1/2 times 0, 0, all 0 minus 3/4. So negative 1/2 minus 3/4 plus 3/4, which is 3/4 times 1, minus 1/2 of 4 plus 2, which is just 0, minus 3/4 of 0 minus 1/2 plus 1, well, that's just positive 1/2. And so making the appropriate little additions and subtractions right here as I go from left to right, this is going to be 1/4, negative 1/2 plus 3/4 plus 3/4 minus 1/2, that's 1/4, and so the total area under that curve amounts to 1/2. Well, that's just what we were looking for, and so we're done.